Understanding variables, the building blocks of programs. In the world of programming, imagine you have a box. You can store things in this box and you can give this box a name so you know what's inside. This box is like a variable. A variable is a fundamental concept in programming and serves as a named storage location in a computer's memory. When we create a variable, we are essentially reserving a space in memory to hold data. Variables are essential because they allow us to write programs that can work with different values. For instance, if we were writing a program to calculate the area of a rectangle, we could use variables to store the length and width of the rectangle. This way, our program could calculate the area of any rectangle, not just one with specific dimensions. Think of a variable like a label on a container. Just as a label tells you what's inside the container, a variable's name tells you what kind of data it holds. This name is important because it's how you'll refer to the variable throughout your code. To use a variable, you first need to declare it. Declaring a variable means telling the computer to create a space in memory for it. You also need to give the variable a name and specify what type of data it will hold. For example, you might declare a variable called age to hold an integer value. Data types are another fundamental concept in programming. They classify the type of data that a variable can hold. Just as we have different types of containers for different items in real life, we have different data types for different kinds of information in programming. Choosing the correct data type is crucial for writing efficient and error-free code. The data type of a variable determines how the computer interprets the bits, the zeros and ones, stored in its memory location. Different data types have different sizes and structures, and they can represent different ranges of values. Using the appropriate data type ensures that the data is stored and manipulated correctly. Imagine you have a container labeled flour and another labeled sugar. You wouldn't store sugar in the container labeled flour because it would lead to confusion and incorrect results when baking. Similarly, using the wrong data type in programming can lead to unexpected outcomes or errors. Understanding data types is crucial for writing reliable and efficient programs. By selecting the appropriate data type for each variable, we can ensure that our programs handle data accurately and efficiently, leading to more robust and predictable software. Integers and floats are two fundamental data types used to represent numerical data in programming. Integers, as the name suggests, represent whole numbers, both positive and negative, without any decimal points. On the other hand, floats, short for floating point numbers, are used to represent numbers with decimal points, allowing for greater precision in calculations. Integers are ideal for situations where we need to represent whole numbers, such as counting the number of students in a class or tracking the score in a game. They occupy less memory space compared to floats, making them more efficient for storing whole numbers. For instance, if we were to store the number of products in a store's inventory, using an integer data type would be the most appropriate choice. Floats come into play when we need to work with numbers that have fractional parts, such as calculating the average temperature over a week or representing the price of an item with cents. Their ability to store decimal values makes them suitable for applications requiring higher precision. For example, scientific calculations often involve very large or very small numbers with decimal points, making floats the preferred data type. Choosing between integers and floats depends on the specific requirements of the program. If we are dealing with whole numbers and memory efficiency is a concern, integers are the way to go. However, if we need to represent numbers with decimal points and require higher precision, floats are the better choice. In the realm of programming, strings and booleans are two essential data types that handle different kinds of information. Strings are sequences of characters used to represent text-based data, while booleans represent truth values, either true or false. Understanding these data types is crucial for working with various types of information in our programs. Strings are incredibly versatile and are used extensively in programming for tasks like storing user input, displaying messages to the user, and working with text files. For example, if we were building a program to store a user's name, we would use a string variable to hold the sequence of characters that make up their name. Strings can also contain numbers. but they are treated as text rather than numerical values. Booleans, on the other hand, are like a light switch that can be either on or off. They are commonly used in conditional statements, where the program needs to make a decision based on whether a condition is true or false. For instance, we might use a Boolean variable to track whether a user is logged in or not. If the user is logged in, the Boolean variable would be set to true. Otherwise, it would be false. The ability to represent text and logical values through strings and Booleans greatly expands the capabilities of programming languages. Strings allow us to work with and manipulate text-based data, while Booleans enable us to create programs that can make decisions based on logical conditions. Mastering these data types is essential for developing more complex and interactive programs. Section 5. Declaring and using variables. Assigning values and following best practices. Declaring and using variables effectively is crucial for writing clean and maintainable code. To declare a variable means to inform the computer to allocate a space in memory for it. When declaring a variable, we typically specify its data type and assign it a meaningful name. Assigning a value to a variable is done using the assignment operator, which is the equals sign. This operator takes the value on the right-hand side and stores it in the memory location associated with the variable on the left-hand side. For example, the statement age equals 25 assigns the value 25 to the variable age. When choosing variable names, it's essential to follow best practices. A good variable name should be descriptive, indicating the purpose or content of the variable. For instance, instead of using a generic name like X, it's more helpful to use a name like student count if the variable stores the number of students. Consistency in naming conventions is also crucial. For example, if you're using camel case like student name for variable names in your program, stick to that convention throughout the code. This consistency enhances code readability and makes it easier for others and yourself in the future to understand the purpose of each variable. Section 6. Arithmetic expressions, performing calculations in code. Arithmetic expressions are fundamental components of programming, allowing us to perform mathematical calculations within our code. These expressions combine numerical values, variables, and operators to produce a single numerical result. Understanding how to construct and evaluate arithmetic expressions is essential for performing various computational tasks. Operators are symbols that represent specific mathematical operations. Common arithmetic operators include addition, which is the plus sign, subtraction, which is the minus sign, multiplication, which is the asterisk, division, which is the forward slash, and modulo, which returns the remainder of a division operation. The order of operations, often remembered by the acronym PEMDAS, dictates how an expression is evaluated. Parentheses have the highest precedence, followed by exponents, then multiplication and division from left to right, and finally addition and subtraction from left to right. Section 7. Conditional statements. Making decisions in programs. Conditional statements empower our programs to make decisions based on specific conditions. They introduce logic and control flow, allowing different blocks of code to execute based on whether certain conditions are met. The most common type of conditional statement is the if-else statement. An if statement evaluates a condition, and if the condition is true, the block of code within the if statement is executed. If the condition is false, the code within the if block is skipped. For example, we might use an if statement to check if a user's age is greater than or equal to 18. If it is, the program might grant access to certain features. Otherwise, it might display a message saying, "Access denied." An else statement can be added to an if statement to provide an alternative block of code to execute if the if condition is false. This way, we can handle both scenarios, when the condition is true and when it's false. For instance, we could modify our previous example to display a message saying, "Welcome," if the user's age is greater than or equal to 18, and you must be 18 or older to access this. If it's not, conditional statements are essential for creating programs that can respond differently based on various inputs or conditions. They introduce decision-making capabilities into our code, making it more dynamic and adaptable to different situations. Section 8. For loops repeating code a specific number of times. For loops provide a structured way to repeat a block of code a predetermined number of times. They are particularly useful when we know in advance how many times we want to iterate over a set of instructions. For loops consist of three parts: initialization, condition, and increment or decrement. Initialization sets the loop counter to its starting value. The condition is checked before each iteration of the loop. If it's true, the loop continues to execute. The increment or decrement part updates the loop counter after each iteration, usually to move closer to the condition becoming false. For example, if we wanted to print the numbers from 1 to 5, we could use a for loop that initializes the loop counter to 1, sets the condition to continue as long as the counter is less than or equal to 5, and increments the counter by 1 after each iteration. The code within the loop would print the current value of the counter, resulting in the output 1, 2, 3, 4, 5. For loops are valuable tools for tasks involving a fixed number of repetitions, such as iterating over elements in a list, performing calculations a specific number of times, or generating patterns. Their concise syntax and predictable behavior make them a cornerstone of iterative programming. Section 9. While loops repeating code based on a condition. While loops offer another approach to repetition in programming, allowing us to execute a block of code repeatedly as long as a specific condition remains true. Unlike for loops, where the number of iterations is known in advance, while loops provide more flexibility when the termination condition depends on factors that might change during program execution. The syntax of a while loop is straightforward. It consists of the keyword while followed by a condition in parentheses. The code within the loop will continue to execute as long as the condition evaluates to true. It's crucial to ensure that the condition eventually becomes false. Otherwise, the loop will run indefinitely, leading to an infinite loop. For instance, we might use a while loop to keep prompting a user for input until they enter a valid value. The loop would continue as long as the input is invalid, and once a valid input is provided, the condition would become false and the loop would terminate. While loops are particularly useful for scenarios where the number of iterations is not known beforehand, such as reading data from a file until the end is reached, or simulating a process that continues until a specific event occurs. Their ability to adapt to changing conditions makes them a powerful tool for creating dynamic and responsive programs. Section 10. Functions and subroutines. Organizing code into reusable blocks. Functions and subroutines are essential building blocks of well-structured programs, allowing us to break down complex tasks into smaller, more manageable units of code. A function is a self-contained block of code that performs a specific task and can be called from other parts of the program. Defining a function involves giving it a name, specifying any parameters it requires, and outlining the actions it should perform. When a function finishes executing, it can optionally return a value to the part of the code that called it. Subroutines are similar to functions, but typically don't return a value. They are often used for tasks that involve modifying data or performing actions without needing to send a result back. Functions and subroutines offer several benefits. They promote code reusability, as we can define a function or subroutine once and call it multiple times from different parts of the program. This eliminates code duplication and makes our programs more concise. Moreover, functions and subroutines enhance code modularity. By breaking down a large program into smaller, self-contained units, we can make our code easier to understand, debug, and maintain. Each function or subroutine can be tested and modified independently, reducing the likelihood of introducing errors in other parts of the code.